Hi, welcome to lecture 8 of Intro to Modern AI. Today we're going to talk about neural networks, and in particular, we're finally going to move on from linear models to a class of model that people, at least as a large component, really use in modern AI methods. So in particular, we're first going to talk about where neural networks fit into machine learning, where neural networks fit in machine learning. So we've talked a lot about machine learning so far, and I want to situate neural networks kind of in that framework. Then, by way of kind of introducing neural networks, I'm going to talk about linear models. So back to linear models for a moment, but linear models with features. These are going to be more expressive than traditional linear models, and they will form the basis for how we think about building neural networks conceptually. We'll then talk about learning features, which will be how we think about neural networks, and this will actually lead us to neural networks. Then we'll talk about a property of neural networks, which is, we're not going to spend too much time on this, but conceptually it's good to sort of see this at least once. We're going to talk about a property of neural networks called universal function approximation. And that's a bit of a mouthful, but it basically just means that, at least in theory, universal function approximation, at least in theory, neural networks are able to represent any function. And we'll talk about what that means, but we'll also talk about the limits of what that means, because that's actually not that deep a statement. It just means you can basically overfit to any possible function if you have a large enough neural network. But it has some relevance, so we'll cover it at least intuitively. And finally, we'll end talking just at least briefly about deep neural networks. Why we might want to go beyond a simple two-layer network, which is what we'll introduce at the start, to talk about deeper neural networks. Neural networks. Okay, let's jump in then and get started talking about kind of where neural networks fit in. So where neural networks fit with ML. All right, now, I guess I wasn't gonna avoid talking about it for too long, but remember our three components of machine learning models. We have our model, or really machine learning algorithms as a whole. We have our model, we have our loss function, and we have our optimizer, or the optimization procedure. And the model, well, I'll start with the second two, actually, because the loss that we used was this cross-entropy loss function. And really, when we start talking about doing machine learning with neural networks, we end up using the same cross-entropy loss. So for the most part, and this is true certainly at least for things like large language models, we're going to use the same cross-entropy loss to train our model. We also talked about optimization, which was SGD, stochastic gradient descent, and we're also going to use that as our optimizer in virtually all modern machine learning. Again, we use slight variants of SGD, things called Atom and other sort of names like this, muon and things like this. But for the most part, these are all based upon basic principles of stochastic gradient descent. But what we are going to do is, rather than talking about linear models, we're going to move to a more expressive function. Because linear models, for all their benefits and for all, we've used them a bunch in this class so far, and we saw they could do things like classify digits, images of digits, and things like this. They fundamentally do have limitations in terms of how complex a function they can represent. And so in moving to neural networks, we really want to talk about moving to a more expressive function, which is able to capture really better and more expressive properties of the underlying data. Or I should say not necessarily better properties, but more expressive properties, able to extract more information from the underlying data than a simple linear model would be able to. Right? And that's going to be basically where neural networks, how we build a neural network for machine learning. So in fact, it's actually quite similar to what we talked about before, because again, the loss and the optimization stay exactly the same. In fact, you can use the exact same code you wrote for a linear model as you do for a neural network. All you have to change is the model. So what is that model? What is a neural network? It's a great name, by the way, a neural network. It's a fancy name, actually, for a relatively simple thing. But how do we get to that neural network kind of model, and what is this exactly? And here, we're going to motivate a neural network by thinking about an extension of linear models. And specifically, an extension of linear models with what we call features. And neural networks will end up being a particular way really to learn such features, at least under one interpretation of what a neural network is. Okay, so to motivate this sort of setting here, I want to start off with a simple example. Really two simple examples. Of classification problems. Classification problems. And in particular, we're going to look at the following kind of visualization of a classification problem. I'm going to think about two axes here, and these are just two different dimensions of an input. So this axis could be x1, this axis could be x2. So we have a two-dimensional input, and I'm just plotting a certain function in 2 dimensions. The details of this are not really important. In fact, I'm actually going to, let me redraw this. I'm going to make clear where the axis is even, in fact. So I'm going to plot it like this. So I'm going to plot it like this, where this is x1 and this is x2. And now I'm going to draw some data points in this space. And we haven't focused too much on this kind of plot thus far in this class. We focused more on sort of, what inputs look like or maybe what the function looks like. But I'm going to draw a plot now that I want to kind of spend some time explaining what it means. And I'm going to draw a bunch of points in this plot, which correspond each point to an individual example in our training set. Or maybe some of these are our training set, some of these are our test sets. So this is a whole bunch of points. Each point, of course, would have, this value for the x-axis and this, or for the x1 value, and this value for the x2 value. So this point represents some specific setting of x1 and x2. And these points in this simple setting are all labeled with class 1. In contrast, these points here are all labeled, or they're a set of different points, and they're all labeled with class 2. And hopefully it is apparent that these two classes can in fact be separated by a line, right? We can draw this line here, and we are in fact able to separate between those two classes of points. And the point I want to make here, the main idea that I'm trying to illustrate by this, is that this line, this particular line here, can be represented kind of over this type of space using a linear model, right? In particular, all we have to do is just essentially define this direction here in 2D space as sort of our first vector, where we have some W here. W would be a classifier. We're taking 2 inputs and mapping to 2 outputs. So our first row here would be W1 transpose, and our other row here would point the other way, and that would just be W2 transpose. And it should be fairly clear that if I take the inner product of any point on this half of the space here, if I take the inner product of this point and this line, those points down here will be more aligned with W2, or they'll have a higher inner product with W2 than with W1, and so they'll be classified as one class. Similarly, all these points up here will have a higher inner product with W1 than with W2, and so they wind up having, basically, they will be classified as class 1 under this classifier. Right, and that's the basic idea of something like this. It's the basic idea of a linear classifier. In fact, if you sort of visualize all possible linear classifiers in 2D space, it leaves us without a bias term, so just a linear classifier like Wx, right? So if I just take W and apply it to x1 and x2, this would be essentially a linear classifier, and they all represent some line, in fact, the line in this case that goes through the origin, that separates those 2 sets of points. But now I want to draw another example of a classification problem. And that one looks like this. That one looks like, say, all my examples from class 1 are here, and all my examples from class 2 are kind of out here. It should be fairly clear now that no matter where I draw a line like this, right? Because I realize there's 2 lines in the previous plot, but to be very clear, kind of this is the separating line here that divides the positive and negative class, and you achieve that by these particular weights. So our separating line that sort of divides the 2 classes is always a line that goes to the origin. It kind of doesn't matter where you draw this line, right? No matter where you draw this line, that way or anything like that, you'll never be able to separate the x's from the o's here. Right? There's no linear classifier that can actually separate these points. So I'll write that down. No linear classifier can really classify these points with high or with perfect or high accuracy. With high accuracy, right? So that's the intuitive idea here about the limits of linear classifiers. We're able to have some sets of points where we can kind of separate out these points, and there's other examples here where we really can't do so. To be clear, maybe I just want to mention the fact that up here, I'm talking about W equals this thing. This is just sort of an additional, this part here was just saying there's what we do with this classifier is multiply it by x. Okay, but there's no classifier, no linear classifier that can separate these points. Now though, I want to conceptually, and maybe I'm going to copy this slide over here. I'm going to copy this figure here to kind of motivate my next point. I want to start talking about a different class of classifier that actually can separate points like this. And I'm in particular going to define the notion of a linear classifier with features. With features. So I'm going to define my model h of x to be equal to some matrix W, not times x anymore, but times some function phi of x. Okay? Where phi here is just some mapping from our input space Rn to some other space Rd. We'll give some examples of this in a second. I'll give some examples actually for this particular instance of or what features would actually make that thing linearly separable. But conceptually, this is our classifier. And here, of course, to make this sort of the sizes work, W would be a matrix which is K by D now, because we want to transform our D-dimensional input, really our D-dimensional set of features, into a K-dimensional output. That's the number of classes we have. Okay, so let's think a little bit about what features might work here. I'm being very kind of abstract here. This is just some set of features or some sort of function that takes as input examples in our input space and produces some other set of features. So let me actually talk about one such set of features. And the example I'm going to talk about here is I'm going to define my features of x for this example to be equal to x1 squared, x2 squared, and the constant 1. All right, so this is a function that maps here our inputs in dimension, I should say really R2, that's our input dimension, to outputs in R3. Right, because this function here just takes two-dimensional input and its output, and to be clear, I'm just defining this manually, right? I'm just sort of giving an example of one such function. And I'm defining it this way. And my claim is that with these features, a linear function can classify this data. So let's look at this in a bit more detail here. And again, the high level point, don't worry too much about this particular example. It's a contrived example. Does data really look like this? Not necessarily, right? This is one particular such example. But my claim here is that we can, in fact, classify this data, this exact data here, when we use a linear function applied to these features. So let's just see that a little bit over here. And I think I'm going to copy this again. I'm actually going to copy a few different things here. I'm going to copy both this and the features that we're going to use. I'm going to copy, oops, I keep selecting the wrong tool here. There we go. I might have to clean it up a little bit on the next slide. But let's see what this looks like again. Okay. And I don't want to spend too much time on this because, I think ultimately this is a very sort of simple example, and again, it is a bit contrived. But all I want to do here is just talk about what's kind of the representational power of a model like this. And to do so, I'm going to sort of say that let's even assume here that this radius, just to make this a little bit more concrete, let's assume that radius here is equal to 1. So the radius, don't worry, I'm not even going to write r. Let's just write the radius here. So let's assume that we're trying to represent the function where all points inside The unit circle are classified as class 1, and all points outside the unit circle are classified with 0.2. Now, what we're going to do here is we're going to define a W matrix. Actually, I'm going to use my blue color for that, for math. We're going to define a particular form of W matrix. So again, our function here is going to be h of x is going to equal w times phi of x. And we're going to use this particular set of phis there. And so what that is equal to then is some matrix, and it's going to be, in fact, in this case, a 2 by 3 matrix, times this term here, x1 squared, x2 squared, and 1. Okay? And we want this quantity if we are inside this circle here. So if we're somewhere in here, we want the inner product of the first column, the first row and this example to be greater than the inner product of the second row and this example. All right, so how do we go about actually doing this? Well, obviously, the thing we're trying to incorporate here is we want to say that if x squared plus y squared is less than 1, we want to classify it one way. If x squared plus y squared is greater than 1, we want to classify it a different way. So let's just sort of represent this very kind of naively. Let's take our examples here to be, well, we want this quantity, we want the second quantity to be large if x squared plus y squared is greater than 1. So let's just make these examples here sort of a 1, a 1, and a negative 1. Right? So if this, and then we'll make the first row, by the way, just the negative of this. We'll make it -1, -1, and 1. And let's consider what happens if a point is sort of within this circle here. So if a point's within that circle, then x squared, so for these points here, let's draw it like this. For these points here, we have x1 squared plus x2 squared is less than 1. What that means is, if we look at the inner product of this row and this column, what is that equal to? Well, that's just going to be equal to I'm going to give it a certain example here because this is only for a particular example. Let's do this color. That would mean the second column would be equal to x1 squared plus x2 squared minus 1. And we don't know what that is, but we know it's some term less than 0. Oops, I'm blocking my own view there. Hang on. Let me move this down. In contrast, of course, because the first row is just the negative of that, this would be sort of negative x1 squared minus x2 squared plus 1. We know that would be greater than 0. So whenever this point is within the unit circle, this term is bigger than that term, and otherwise we classify it as class 1. On the flip side, if we have this whole thing here being greater than 1, if this thing here is greater than 1, then, well, x1 squared plus x2 squared minus 1 is greater than 0. Keep getting the wrong colors here. Right? And the opposite is true for the first column, for the first entry in that column. Right? So this particular classifier here, and again, this is, you can go through this example if this was confusing, but this particular classifier here is able, when you use these features, to find a linear function, to sort of represent a linear function that is able to classify this data, to classify all this data in here as one class and all the data outside the circle as another class. And again, this is a particular example. I don't want to dwell too much on this example, but the key point that I want to make here is that when you introduce a linear function with features, you are able to represent more complex functions. So let me sort of write that down. So this is the takeaway from all of this. When you use a linear model with features, we can represent more complex functions. More complex. And even if the details in that previous section were a bit confusing, this is really the take home, is that linear functions applied to a set of features are more expressive. And in fact, I'll even go beyond that and say, for a very long time, implementing, so up until I would say, in the, now I want to be careful here because neural networks were in fact very old. They were invented, you could argue they were actually invented before, with the McCulloch and Pitts neurons, right? But neural networks were actually quite popular in machine learning in the 80s, well before the 2000s. But I would say that sort of until 2000s, the state of the art, and I'm going to put state of the art here in quotes because you could argue this wasn't really the state of the art, but at least what people were sort of really doing in machine learning was using linear models with handcrafted features. So we developed features for things like images, for things like sound, for things like email classification, all this stuff. People would hand design features and then apply a linear classifier on top of that. And at least when I entered the field of machine learning, this really was the state of the art. This is what most people, or at least a large fraction of models, were doing, especially when they had to be fast and things like this. People would kind of manually extract features and then apply a rather simple linear classifier on this, using whatever features they could kind of think up. But it does seem rather kind of, I would say, cumbersome and hard to do. I mean, in this last slide, I seemingly just pulled this kind of out of nowhere, right? And if you're sort of paying attention, you might kind of guess that, look, this data here is representing kind of a circle, so it makes sense to have features that encode, elements of x squared, because circles are represented in terms of the square of the different elements. So it kind of makes sense in retrospect, but where on earth did I come up with this? And for some new problem, how would you develop a set of features that were a good fit for your particular problem? And this was a hard thing. This was actually a lot of the work in machine learning went into designing these features manually, which does seem like rather maybe not the best use of time. And so this motivates the approach we'll talk about next, which is kind of one way of introducing neural networks, which is essentially as a way of automatically learning features. And this is going to lead us to a class of model that we'll call neural networks. Okay, so at an intuitive level, the idea I'm going to use to motivate the construction of a neural network is kind of the simple question, which is that why don't we learn features? Why don't we learn the features phi? So in other words, we have our model, h of x equals w phi of x. Yeah, we'll actually again write this in blue. H of x equals w phi of x for some function phi. Why don't we just, and we're already learning the w, right? We're already using w. We parameterize it and we optimize it with gradient descent. Why don't we find some function that we can also optimize with gradient descent? That seems like a good idea. And so in fact, we're going to do exactly that. And remember, phi is a function which maps from our input space Rn to some arbitrary other dimension, which I'm just calling Rd here. D here can of course be arbitrary, right? It's just some dimension. And you obviously, when you do this, have to change W to be K by D, because now it's mapping D-dimensional vectors to K-dimensional vectors, the number of classes we have. So why don't we just learn this function phi? And that's exactly what we're going to do, in fact, with neural networks. But how should we go about doing it? And the first thing I'm going to sort of try, which is going to be attempt number 1. I should be clear here, this attempt is not going to work for a reason that will become very obvious soon. But, when we needed a model that mapped n-dimensional inputs to k-dimensional outputs, the first thing we tried was a linear model, right? Just a matrix that maps between these two spaces. Why don't we just use a similar linear model as our feature function? So explicitly, why don't we pick h of x to be equal to some matrix w2 phi of x? I'm going to start using w1 and w2 now because there's going to be 2 linear matrices here, where phi of x is just equal to w1 times x. We could do this, right? This makes total sense, and it seems like a reasonable choice of features. Here, of course, w2 would be a k by d matrix, and w1 would be a d by n matrix. This is a valid mapping, right? This is a valid transformation of inputs to outputs. But there's a problem here. So there's a problem with this particular representation. With these features. And the problem, hopefully, is fairly apparent if you sort of spend some time kind of looking at this particular form for a little while. And the problem is, if we simplify the above, so if we take these two expressions and just combine them, then what we get is h of x would just equal w2 times w1 times phi of x. And by the associative property of matrix multiplication, we can just take these two matrices here, so this is a k by d matrix times a d by n matrix, and we can just write this as some other matrix w times x. Oops, sorry, this should be x here. No more phi, right? Because phi is equal. Phi, of course, is equal to w1 times x. So if this was phi of x, that's just equal to w1 times x. But this is equivalent to saying there's just some other matrix wx. It's just the product here of w1 and w2 and w1. So in other words, we've gone through all this work, but we've wound up with something which is just the same as a linear model. Right? We haven't actually, what we've ended up with is in fact just a linear model. We haven't gotten any more expressivity out of this particular choice of features. And that stems from the fact that you can distribute, or you can do the matrix multiplication, not distribute, you can associate, it's associative, so you can do the matrix multiplication in whatever order you want. And so this matrix times these features is in fact the same thing as just a matrix times our original inputs x. Okay, so that's not going to work. But the truth is, even though this doesn't work, and in fact this is definitely not something you want to do, it's just the same as a linear model, something very similar to this does work. So we're going to have attempt number 2. Which is going to do the following. We're going to actually take something very similar here. We're going to take h of x to be equal to w2 times phi of x. And I'll pretty soon stop writing phi at all because I don't really need to write it in some sense. But I'm going to set phi of x equal to w1 times x. But I'm going to additionally apply some function sigma, where sigma here is some nonlinear function. Some nonlinear function. Sigma mapping scalar values to scalar values, and really this is when I write this and say sigma is a scalar function, what I of course really mean there is that sigma is a scalar function, which because this isn't its argument's a vector, what I really mean here is that sigma is being applied element-wise. It's being applied element by element to every entry to vectors. It's being applied to every element in that vector. And now the old simplification doesn't work anymore. So in other words, this is no longer, I should write this as a subcategory here. So this is no longer equivalent to a linear model. And that's because if you look at the form that h of x takes now, h of x is equal to w2 times this sigma of w1x. And we can't play that same trick as before. There's no single matrix, or there's no sort of single matrix, linear matrix, that can represent this function when you have this nonlinearity here. And in fact, this is going to be, for certain types of nonlinearities, or really for any nonlinearity almost, this is in fact called, in this case, a two-layer, because there's each layer is sort of considered one matrix here, one matrix transformation. So this is called a two-layer neural network. And that's really all there is to a neural network. It is a repeated application of linear layers like this and some nonlinearities applied element-wise. So before I sort of move on to some properties of neural networks, I just want to kind of define what I mean there. And then also talk a little bit about kind of what we actually use here for the nonlinearities. So which nonlinearities are we actually going to use? What function do we actually use for that, at least in practice? So first of all, I just want to define this term now, since I'm going to use this really throughout the rest of the lecture. And maybe I won't even say a neural network here. I'll in fact say sort of a two-layer, fully connected neural network. Neural network is just this function this h of x equals w2 sigma w1 times x. Now, more generally, I do want to kind of be a little bit careful here because neural networks is a very overloaded term. It's also a sort of a great marketing term, right? It sounds very, very fancy and complex, like we're modeling the brain and things like that. And to be clear, with the right sort of choices for some of these things, and if you really squint, a lot of the kind of initial framing of these models was in fact developed to talk about things like modeling the brain, but this is a very rough analogy. So more generally, what a neural network really means these days, I'm going to put neural network in quotes here. What it kind of really means these days is just a series. I shouldn't say a series because they can kind of also have multiple different loops and stuff. But a series, I'll still use the word series, though I'm using it. It doesn't have to be sort of one after the other. It can also have kind of branches and such in this function. But it's basically a series of differentiable functions applied to transform the input. Transform the input to predicted outputs. And of course, this function here would be, in this notation, a neural network. So there's a lot of other things, right? In fact, so even a linear model would be a neural network. You typically don't refer to a simple linear model as a neural network, but basically any other series of operations that includes some nonlinear function would in fact be a neural network if you apply a sequence of operations to produce an output from an input. That's in some sense just kind of how broad this term has come to be, and we're going to kind of use that definition. The last thing I want to say before sort of moving on is the choice of nonlinearity. Because, I've defined linearity. I've defined this sort of thing as, some nonlinear function, some nonlinear function applied element-wise to its input. And I just want to define a few possible choices there that are rather common, in fact. So one of the more common choices here that people use is called the ReLU nonlinearity. And this is just the function sigma of x equals the max of 0 and x. If I plot that, hopefully I have space to plot all these things, but if I sort of plot that, oops, I should probably have a negative axis there. If I plot that like this just looked like this function, so it looks like a function that is 0 on the negative portion of the axis and then becomes positive here. There's many other nonlinearities I could use. For example, there's also the sigmoid, which is this function, x equals 1 over 1 plus e to the negative x. The exact form doesn't really matter. What matters here is really the graph. It's something that looks like this. On the negative axis, as you go further and further negative, this approaches 0, and then it kind of asymptotes at 1 here. So this would be the value 1 at this axis here. That is a sigmoid nonlinearity. And then there are many others. There's the, for example, tan H nonlinearity, which is just sigma x equals the tan H function, which just happens to be equal to e to the x minus e to the negative x over e to the x, e to the x plus e to the negative x. That looks a lot like a sigmoid, except that its asymptote is not at 0 and 1. Its asymptote is at -1 and 1. So it looks kind of more like this function here. And then people use other ones too. So one thing people use frequently is something called a Silu function. So that's the sigmoid linear unit. Not at all a linear function. It's a very confusing name. But it's basically the product of the sigmoid nonlinearity and x. So this is going to equal, in fact, sigma x equals x over 1 plus e to the negative x. The reason why it's called a Silu is that it actually looks a little bit similar to the ReLU, just kind of like this. It looks sort of like this. It goes down a bit and then it comes up. So sort of a smooth version, in some sense, of the ReLU nonlinearity with a brief negative portion as well. Okay, so that is, actually I should be more clear here, that does go to the origin, to be clear. Because of course when x is 0 here, this thing has to be 0. And so it looks like this. Something like that. You can just plot these if you're curious exactly how they look. But these are the kind of nonlinearities that are actually used in practice by neural networks. Okay, so that's in fact a neural network. A neural network is a function like this, where sigma is typically chosen to be some function like the ones we have here. You know, the ReLU, sigmoid, tan H, Silu, whatever you want. But the point I want to make now, the point I want to talk about now, is intuitively, why does this make such a big difference? Why does including nonlinearity make such a big difference? And the way we're going to kind of justify this is with a very informal statement, to be very clear, a very informal statement of a theorem called the universal approximation theorem. Actually, you know what? I'm going to, in fact, not even call it a theorem. I'm just going to call this in terms of universal function approximation. And the point I want to convey right now is, in some sense, why is a neural network so much more expressive than a linear function? Because in some sense, you know, all we have done is gone from this function here, which I said was, you know, just a normal linear function. There was nothing to this. All we have done is, you know, this cannot represent very many functions, is add a little nonlinearity here. And now I've made the claim that this function here is extremely expressive. In fact, as I will say now, this function winds up being able to represent really any function with slight modifications to this, at least the setup that we have right here. But in practice, this is also an extremely expressive function for representing a lot of neural network or machine learning models that can capture many, many more properties of the data. So in fact, you know, just as an example here, what you will see on your homework is that on this MNIST classification problem, so this is a problem of classifying digits, the best classification. The best linear model, and I'm throwing best in quotes here because, you know, it's approximate here. The best linear model gets about, on the order of about 7.5% error. And the best two-layer neural network, so this is just this function right here, two-layer neural network, gets, again, I should be, now I have to be even more careful than saying the best linear model, but at least the one, at least some that you can build on your homework here, get about, it's around 1.5% error. So we're able, and as a percentage here, there's a huge reduction in error, of course, right? So by doing just this, you know, not only are we able to sort of, in theory, mathematically kind of have more power, we're also practically able to get much better performing classifiers. But what I want to do right now is just give a hint of, in fact, a rather deep result. Well, actually, whether it's deep or not depends really on whether you think sort of basic mathematical statements are deep or not. I actually think it's not that deep a result, in that it's just sort of saying that you can basically overfit any function with a high enough dimension to your neural network. But the basic idea I want to convey here is something called the universal function approximation theorem. And it essentially says, again, I'm setting this very informally now, is that with a large enough dimension d, so large enough d, that is, again, d here is the dimension of this thing. So it's something's called hidden dimension or inner dimension of the neural network. With large enough d, a two-layer neural network can represent any function over a bounded region. And the way I'm going to sort of not prove this, but give you some intuition about this, is I'm going to think about kind of functions that have a one-dimensional input. So let's think about this function here. Let's think about the function that has some input x and output h of x. If I look, first of all, if I look at linear functions, so if I'm constrained to sort of say that h of x equals a linear function of this, and I'll even see here I will even add say w times x. I'll even add what's called a bias term, an additional term, that just is a constant term you add to this function. But this function basically can represent only lines with some slope and some intercept to the x-axis there, right? Or y-axis. So this is the slope is basically how steep this line is, and then the y-intercept is sort of where it crosses that. That's given by this term b. This linear function can only represent those sorts of functions. But it turns out that if I have any function, or rather if I have a two-layer network, I can represent any function at least over a certain bounded region. So if I have any function like this, I can get arbitrarily close to representing this function with a two-layer neural network. So let me see sort of, and that could maybe make a more complex function just for the sake of it. That is a function there. I'm not meaning to overlap in case I'm doubling back on myself. That's an unintentional. But if I have some function like this, I can construct a neural network that approximates this. So let's see just briefly, intuitively how this works. What I'm going to do here is I'm going to kind of break down this function in a fashion that can be represented via a neural network. So, in fact, let me move them over a little bit. Okay, so remember, we're going to try to represent this function here as actually a slightly more, I'm going to make one minor adjustment, but you can always represent this kind of with a few more layers and do this in a slightly different way. I'm going to make one little adjustment to this function here. I'm actually going to define my neural network here to be equal to h of x is going to be equal to W2 times, I shouldn't use phi there, I should meant sigma times W1 x. I'm also going to add this bias term here. So let me sort of define all these sizes. So x here is going to be, as our input, one-dimensional. And that means that W1 would be a matrix which is d by 1, right? It takes a one-dimensional input and maps to some d-dimensional vector. B here would be a vector in RD because I need to, this term is going to be a vector in RD. I want to add some term to that, so that also has to be a vector in RD. And then this term here is going to be equal to a matrix, which is going to be the output dimension, which is just 1 times d. So again, this is my output here. I, in fact, have a, in this case, just a single dimensional output, and this is my input x. Okay, to be clear here, this is not, this is my representation. I'm going to use this representation to represent this function. Actually, you know what, let me redraw this function in a different color to make clear that I am not trying to say this function is equal to that. I'm going to have some arbitrary function here, and I'm going to represent it with this function here. Now, without getting into too much detail, and I'm also going to use, by the way, I should say, the ReLU nonlinearity. So I'm going to say that sigma of x, maybe I'll write sigma of z, just to make it clear this is some arbitrary input, is the max of 0 and z. Okay, so how do I actually go about representing some arbitrary function here as a set of these things? Well, the idea here is that h of x can also here be written, well, I'm writing it as W2 times this thing, W2 times this thing, but really what that is that is just going to be the sum from I equals 1 to d, right? Because I'm just taking an inner product. This thing here is really just a vector. So W1 is just a row vector times this column vector here. I'm just representing them as matrices. So it's going to be equal to the sum from I equals 1 to d of some term, and I'll just to be a little bit more clear here, maybe rather than calling this thing W and W2 and W1, because that requires a bit of too much notation here. I'll call this A, and I'll call this one W. So of course here now A is going to be effectively a vector, and W2 is going to be a row. So A is basically a column vector, and W2 is a row vector. So this will be equal to Wi, where here I is just the ith component of W, times the max of 0 and this thing. But I'm going to write that as sort of the max of 0 and AI times x plus BI. Okay? So that's sort of all that we really have here. And that is, in fact, just another way of writing this function. So what do those functions look like? Well, what those functions look like is they are kind of, at every point, equal to 0 beyond some point, and then they have some slope. And that slope can be positive or negative depending on, the settings of A and W there. It can look like that. And while I'm not going to sort of prove this, it should be fairly obvious, after thinking about it for a bit, that if you kind of take this function, or you take functions like this, and add them up, what you can kind of get is, okay, so I can add another version here, which has essentially, it goes 0 for longer, and then looks like this, etc. If I add up a whole bunch of these functions, I can, in fact, get a function which essentially can represent any piecewise linear function. So any function that I want, I can represent kind of any function that looks like this by adding up enough of these functions. And then by sort of forming a smoother and smoother approximation of our original function, I can start to approximate this function kind of arbitrarily well. Now, to do so, I might need a very high dimension. I might need a very high d, because each d basically gets me one such linear function like this. But the basic idea is that I can add up a whole lot of these and get better and better approximations. It would look kind of like this, right? So it would sort of look like this function at first, maybe. And by selecting more and more points, i.e. adding more and more linear functions, I can get better and better approximations to any function. So that is the idea behind universal function approximation. I don't want to dwell on this too much because, again, I think it's a nice property, but in order to actually achieve a good approximation for any arbitrary function, you need very, very large dimension d, even just for a one-dimensional input. And as you have higher dimensional inputs, you have to do more and more. You're basically overfitting to this function. It's not an interesting function. It's just sort of a piecewise approximation to whatever underlying function you want. Okay, so again, if the details there were a bit too convoluted, the key underlying point is that neural networks with large d can represent any function basically by more or less by piecewise, by approximating explicitly approximating each portion of the function. Now, there is no notion here of generalization, of sort of how well this predictions or these models will generalize to new data. There's really no machine learning at all in this theorem. It is just sort of a mathematical theorem. You have to make a few more assumptions, by the way, to sort of make this sort of rigorous mathematically. But it is just a mathematical theorem that's talking about the expressive power of these networks. Okay, so again, that's somewhat of an aside, and I kind of want to emphasize that this is a bit more mathematical than we're going to be for most of the course. We really don't want to dwell on this too much because it's a very trivial theorem statement in some ways. The thing I want to end with, though, before we sort of spend the next lecture talking about how we actually implement neural networks, is to at least mention deep neural networks. Because what I've defined so far is what's called a two-layer neural network. So what we have so far is a two-layer neural network. But in practice, we're going to use much deeper neural networks, which just wind up being kind of, at least in a or in some sense, a repeated application of these types of networks or other modules, other modules, other layers, which we'll talk about later. So this is we'll just cover this briefly because I think that the actual form of real deep neural networks is not just a repeated application of kind of the same thing, but I want to give some examples of sort of what this can look like. So again, our two-layer neural network is just this function, W2 sigma W1 x. This is called, among many things, also called, by the way, a multi-layer perceptron. There's great names for these things. That comes from the fact that first kind of linear model way back in the day was called a perceptron, and so this is a multi-layer, in fact, a two-layer perceptron. It's also sometimes called a fully connected network. Actually, by the way, also one thing I'll just mention here is that multi-layer perceptron is sometimes abbreviated MLP. So if you see something referred to as MLP in a neural network context, that's just a simple neural network like this. It's also called a fully connected network, and there's many other names for this. But the point I want to make now is that these kinds of networks can actually be extended to be much more complex functions. And one simple example, which I want to give, is just a multi-layer for layers greater than 2 neural network. In fact, I want to say a multi-layer MLP. I know that's multi-layer, but forgive me. I know that the M here stands for multi-layer. It's MLR, MLP. No one will blink if you do say multi-layer MLP. So what this would be, for instance, is just, and I'm not going to sort of define each term here, but it could be sort of just a repeated application of the same idea. So we have some WL times sigma of WL minus 1 times sigma, etc., times W2 of W2 times sigma of W1 times X, right? And you would just sort of repeat this same thing many, many times. This would be an L layer MLP. Right. You can define this sort of recursively and things like this and sort of, define intermediate terms. The one thing I want to say here is that there is one term I'm going to use a lot when talking about neural networks and deep networks broadly. And I should say that for real deep networks, we will not just use kind of repeated application of this, but in fact, as we'll see next time, sort of repeated application of a linear layer and an element-wise nonlinearity. We'll use more involved things like self-attention layers, they're called. Other networks use things like convolutional layers and stuff like this, which we're not going to cover in this course, but we will use much more involved layers than just this. In fact, no real network just has a form like this. But intuitively, it's kind of worth emphasizing that we can apply all the same techniques that we're using for two-layer networks, and in fact, for linear models, really, the same optimizer, same loss function, as we do for deeper networks like this. One bit of terminology I want to mention is that intermediate layers, so intermediate terms, so, something like this, say, that term there. All intermediate terms you compute in a network, a neural network, are sometimes called, well, they're called a whole lot of things. They can be called activations. They can be called representations. hidden layers, hidden units, and there's probably more that I'm forgetting here, but we use a lot of different bits of terminology to cover just this notion of some intermediate term that's computed in a network. And I'll use that terminology sometimes, so I just wanted to mention it here. Before I do, though, because this is actually the extent of neural networks. This is it. This is the function that we're going to use. Or more complex variants, but even very complex networks, by the way, will have will sort of build upon, so that even the things that power modern LLMs actually build upon two-layer networks. So inside of them, they have a bunch of applications of these two-layer networks as well. So we're going to stack a lot of these things together. And the natural question that we sort of might want to ask is, why do we use deep networks? Right? I just argued to you, really in this sort of very informally, but I just did argue to you that a two-layer neural network was a universal function approximator. So we're able to represent any function using just a two-layer network. So why would we want to use deeper networks? Why would we want to kind of keep doing this? Why go beyond just a two-layer network? And there are a few reasons for this that are sort of all reasonable justifications for why we might want to use deeper networks, which I'm just going to mention here. I'm just going to sort of mention why we might want to do this. The first is by an argument about efficiency of representations. So efficient representations. And I'm not going to prove this, but the core idea here is that some functions can be represented, or I'll just say can be expressed, with fewer parameters, fewer weights, parameters, when using a deep network than a two-layer network. A classical example, which I'm not going to get into, is what's called the parity function. So if I want to take an input and say my input was all zeros and ones, and I want to create a function that predicts whether there's an even or odd number of zeros and ones, it turns out that if you do this with a two-layer neural network, you will need a number of hidden units, d, that is exponential in the size of the input. That's just a fact from sort of circuit theory from kind of basic computer science circuit, or basic theoretical computer science circuit theory. On the other hand, if you allow a multi-layer network, you actually can do the same thing with only a linear number of hidden units, which we're not going to prove here. You basically do it by sort of setting up kind of a competition, sort of one function that takes sequences of two and determines whether there's an even or odd number of elements there, and then the next one, and then you sort of have kind of something that looks like kind of a bracket in this case. But we're not going to kind of cover that. Just you'll have to sort of take my word for that. But this is the reality, right? There are a lot of functions that we are able to express more efficiently if we use a multi-layer network than if we use just a two-layer network. The next property, or the next reason why we kind of might want to use deeper networks is the analogy with the brain. Now, at least in this class, I do tend to shy away from too many analogies between neural networks and our neural network. We still don't understand a lot about how the brain works, certainly, but we know enough to know that the brain is definitely not a function like this. Right, that is a bad approximation to the brain, especially if you have, nonlinearities like the ReLU nonlinearity. And we also know that the mechanism by which we learn these sorts of networks does not appear to resemble what happens in the brain. So I do want to make even the name neural network clearly kind of evokes similarities to the brain. And I don't want to dismiss this either, right? A lot of the original development around neural networks was very inspired by people trying to understand and think about how learning might work in the brain. So it's been a very sort of useful and fruitful analogy through to the development of a lot of neural networks. And just like the brain has multiple layers, so we sort of take inputs like the things our eyes see, and they go through multiple stages of processing before they actually reach our cortex and things like this. And this is true about the brain, but it's also in some sense kind of a weak analogy. So I want to make this analogy, but I also don't want to go too overboard on this because neural networks are not, in fact, how the brain, a good model of the brain. But I'll just say, brain uses multi-stage processing of inputs. Maybe we should too. And then finally, I also want to just make the argument of empirical performance. And maybe this is actually the best argument in the end. Because when you ask the question kind of why do we use deep networks, the real reason why we use them sometimes for modeling things like large language models and such is that multi-layer networks, they just work better. And what I mean by work better is they generalize better with fewer parameters. Than single layer or single hidden layer, two layer. So if you actually want to build a model and try out different depths, you will find that at least when you start talking about structured models and sort of models that have a little bit of structure built in, we'll talk about that in a couple lectures from now, you get better performance if you use multi-layer networks than if you use simple two-layer networks. And ultimately, I would argue that probably is the real reason why people tend to use deep neural networks. Okay, but that actually is all for today. That is all we're going to talk about when it comes to simple two-layer neural networks. Next lecture, though, we're going to talk a little bit more about how you actually implement these things, some of the details of implementation, because it is true that implementing a deep neural network, when you add the loss function, add the optimizer, does have some additional complexities over just optimizing a linear model. And things like initialization have to be done differently, and we'll talk about those a little bit more next time. See you all then.